right, we've been looking at ways of organizing computations using streams. What I want to do now is just show you two somewhat more complicated examples of that. Let's start by thinking about the following kind of utility procedure that'll come in useful. Suppose I've got a stream, and the elements of this stream are themselves streams. So the first thing might be 1, 2, 3. Right. So I've got a stream, and each element of the stream is itself a stream. And what I'd like to do is build a stream that sort of collects together all of the elements, pulls all of the elements out of these substreams, and strings them all together in one thing. So just to show you the use of this language, how easy it is, I'll call that flatten. And I can define to flatten what we should call it a stream of streams. Well, what is that? That's just an accumulation. I want to accumulate using append, by successively appending. So I accumulate using append streams. Starting with the empty stream. Down that stream of streams. Okay, so there's an example of how you can start using these higher order things, do some interesting operations. In fact, there's another useful thing that I want to do. I want to define a procedure called flat map. Flat map of some function and a stream. And what this is going to do is f will be a stream of elements. F is going to be a function that for each element in the stream produces another stream. And what I want to do is take all of the elements in all of those streams and combine them together. So that's just going to be flatten of map f down S. Each time I apply f to an element of S, I get a stream. If I map it all the way down, I get a stream of streams, and I'll flatten that. All right, well, I want to use that to show you a new way to do a familiar kind of problem. The problem's going to be, this is like a lot of problems you've seen, although maybe not this particular one. I'm going to give you an integer n. And the problem is going to be find all pairs all pairs of integers I and j between 0 and I with j less than I up to n, such that I plus j is prime. So for example, if n equals 6, let's make a little table here. I and j and I plus j. So for, say, I equals 2 and j equals 1, I'd get 3. And for I equals 3, I could have j equals 2, and that would be 5. And 4 and 1 would be 5, and so on, up until I goes to 6. And what I'd like to return is to produce a stream of all the triples like this. Let's say I, j, and I plus j. So for each n, I want to generate this stream. Okay, well, that's easy. Let's build it up. We're going to start like this. We're going to say for each I, we're going to generate a stream. For each I in the interval 1 through n, we're going to generate a stream. What's that stream going to be? We're going to start by generating all the pairs. So for each I, we're going to generate, for each j in the interval 1 to I minus 1, we'll generate the pair, or the list with two elements I and j. Right, so we map along the interval, generating the pairs. And for each I, that generates a stream of pairs. And we flat map it. Now we have all the pairs I and j, such that I is less than j. So that builds that. Now we've got to test them. Well, we take that thing we just built, the flat map, and we filter it to see whether the I, see we had an I and a j. I was the first thing in the list, j was the second thing in the list. So we have a predicate which says in that list of two elements is the sum of the car and the critter prime, and we filter that collection of pairs we just built. So those are the pairs we want. Now we go ahead and we map, we take the result of that filter, and we map along it, generating the list I and j and I plus j. And that's our procedure prime sum pairs. Okay, and then just to flash it up, here's the whole procedure. Right. Map, a filter, a flat map. Right, there's the whole thing, even though this isn't particularly readable. It's just expanding that flat map. All right, so there's an example which illustrates the general point that nested loops in this procedure start looking like compositions of flat maps of flat maps of flat maps of maps and things. All right, so not only can we sort of enumerate individual things, but by using flat maps, we can do what would correspond to nested loops in most other languages. Of course, it's pretty awful to keep writing these flat maps of flat maps of flat maps. Prime sum pairs, you saw, was looked fairly complicated, even though the individual pieces were easy. So what you can do, if you like, is introduce some syntactic sugar that's called collect. And collect is just an abbreviation for that nest of flat maps and filters arranged in that particular way. Here's prime sum pairs again, written using collect. It says, to find all those pairs, I'm going to collect together a result, which is the list ij and I plus j. That's going to be generated as I runs through the interval from 1 to n, and as j runs through the interval from 1 to I minus 1, such that I plus j is prime. So I'm not going to say what collect does in general. You can look at that by looking at it in the book. But pretty much you can see that the pieces of this are the pieces of that original procedure I wrote. And this collect is just syntactic sugar for automatically generating that nest of flat maps and flat maps. Okay. Well, let me do one more example. It shows you the same kind of thing. Here's a very famous problem that's used to illustrate a lot of so-called backtracking computer algorithms. This is the 8 queens problem. This is a chessboard. And the 8 queens problem says, find a way to put down 8 queens on a chessboard so that no two are attacking each other. And here's a particular solution to the 8 queens problem. Right, so I have to make sure to put down queens so that no two are in the same row or the same column or sit along the same diagonal. Now, there's sort of a standard way of doing that. Well, first what we need to do is sort of below the surface, at George's level, we have to find some way to represent a board, represent positions. And we'll not worry about that, but let's assume that there's a predicate called safe. And what safe is going to do is going to say, given that I have a bunch of queens down on the chessboard, is it okay to put a queen in this particular spot? So safe is going to take a row and a column. That's going to be a place where I'm going to try and put down the next queen. And the sort of rest of positions. And what safe will say is, given that I already have queens down in these positions, is it safe to put another queen down in that row and that column. And let's not worry about that. That's sort of George's problem, and it's not hard to write. You just have to check whether this thing contains any things on that row or that column or in that diagonal. Okay. Now, how would you organize the program given that? And there's sort of a traditional way to organize it called backtracking. And it says, well, let's start off. Let's think about all the ways of putting the first queen down in the first column. There are 8 ways. Well, or let's say we'll try the first column. Try column 1, row 1. These branches are going to represent the possibilities at each level. So I'll try and put a queen down in the first column. And now, given that it's in the first column, I'll try and put the next queen down in the first column. Well, that's no good. They're both if I put the first queen, the one in the first column, down in the first row, and then given that, we'll put the next queen down in the first row, and that's no good. So I'll back up to here, and I'll say, oh, can I put the first queen down in the second row? Oh, that's no good. Oh, can I put it down in the third row? Well, that's good. Well, now can I put the next queen down in the first column? Well, I can't visualize this chessboard anymore, but I think that's right. And I try the next one, and at each place I go down as far down this tree as I can, and I back up. If I get down to here and find no possibilities below there, I back all the way up to here, and now start again generating this subtree. And I sort of walk around, and finally, if I ever manage to get all the way down, I found a solution. Right, so that's a typical sort of paradigm that's used a lot in AI programming. It's called backtracking search. And it's really unnecessary. You saw me get confused while I was visualizing this thing. You sort of see the complication. This is sort of a complicated thing to say. Why is it complicated? It's because somehow this program is too inordinately concerned with time. It's too much. I try this one, and I try this one, and I go back to the last possibility. And that's sort of a complicated thing. If I stop worrying about time so much, then there's a much simpler way to describe this. It says, let's imagine that I have in my hands the tree down to k minus 1 levels. See, suppose I had in my hands all possible ways to put down queens in the first k columns. Suppose I just had that. Let's not worry about how we get it. Well, then how do I extend that? How do I find all possible ways to put down queens in the next column? It's really easy. For each of these positions I have, I adjoin queens. I think about putting down a queen in each row to make the next thing, and then for each one I put down, I filter those by the ones that are safe. Right? So instead of thinking about this tree generated step by step, I say, suppose I had it all there. And so to extend it from level k minus 1 to level k, I just need to extend each thing in all possible ways and only keep the ones that are safe, and that'll give me the tree to level k. And that's a recursive strategy for solving the 8 queens problem. All right, well, let's look at it. All right, to solve the 8 queens problem on a board of some specified size, I'm going to write a sub-procedure called fill columns. Fill columns is going to put down queens up through column k. And here's the pattern of the recursion. I'm going to call fill columns with the size eventually. So fill column says how to put down queens safely in the first k columns of this chessboard with a size number of rows in it. If k is equal to 0, well, then I don't have to put anything down. So my solution is just an empty chessboard. Otherwise, I'm going to do some stuff. And I'm going to use collect. And here's the collect. I find all ways to put down queens in the first k minus 1 columns. And that's just what I said for. Imagine I have this tree down to k minus 1 levels. And then I find all ways of trying a row. That's just each of the possible rows, their size rows. So that's a numerate interval. And now what I do is I collect together the new row I'm going to try and column K with the rest of the queens. I adjoin a position. This is George's problem. A joined position is like safe. It's a thing that takes a row and a column and a rest of the positions and makes a new position collection. So I adjoin a position of a new row and a new column to the rest of the queens, where the rest of the queens runs through all possible ways of solving the problem in k-1 columns, and the new row runs through all possible rows, such that it was safe to put one there. Right? And that's the whole program. Right, there's the whole procedure. Right? Not only that, that doesn't just solve the 8 queens problem. Right? It gives you all solutions to the 8 queens problem. When you're done, you have a stream, and the elements of that stream are all possible ways of solving that problem. Right? Why is that simpler? Well, we threw away the whole idea that this is some process that happens in time with state. And we just said it's a whole collection of stuff. And that's why it's simpler. Right? We've changed our view. Remember, that's where we started today. We've changed our view of what it is we're trying to model. And we're stopped modeling things that evolve in time and have steps and have state. And instead we're trying to model this sort of global thing, like the whole flight of the chalk, rather than its state at each instant. Any questions?
It looks to me like backtracking would be searching for the first solution it can find, whereas this recursive search would be looking for all solutions.
Right.
And it seems that if you have a large enough area to search, that the second is going to become impossible.
Okay, that's the answer to that question is the whole rest of this lecture. It's exactly the right question. So you should start, without trying to anticipate the lecture too much, you should start being suspicious at this point. And exactly those kinds of suspicions. Isn't it, it's wonderful, but isn't it so terribly inefficient? That's where we're going. Okay. So I won't answer now, but I'll answer later. Okay, let's take a break.